This example actually comes, example 2, before the constant acceleration part of the booklet. However, I think it's probably the easiest way to think about it. You know, when you do your exam and do all these questions, they're all together. It's not this is this kind of topic, this is this. You have to kind of pick that skill out. And when I see that, this is what I think of. So it says, when it passes point A with velocity 3I, take away 2j. So for me, I'm thinking initial velocity. Again, I generally will always work in column vectors. There's no problem working with I and j as they do in the word solution as well in the book. And passes point B 4 seconds later, so t is 4, with a velocity of 2.5. So effectively a v, like the examples we're going to look at a little bit later on. And then acceleration is what it wants. It says magnitude, it says direction, so we'll need those, but first we need the acceleration itself. So we need to use, I'm just going to use one of the Suvat equations, and I'm going to pick out the one that involves these, so that's v equals u plus at. Okay, and then I'm just going to put those in as vectors. I know some people will rearrange their equations first and put the numbers in, but I generally put in my vectors first. So I use 2.5 here, 3, -2, and it's exactly the same as when we use, put my time first, as when we used Suvat before, except we've got two things effectively working on two lines, if you will. Okay, so for my top line, I've got 2 equals 3 plus 4a. Just use the x just to keep those slightly separate. On the second line, I've got 5 equals -2 plus 4ay. So there's lots of slightly different ways of thinking about this in terms of the i's and the j's and stuff, but this slightly separate lines just makes it, I think, easier. So you can see at the side here, ax should equal to 2 take away 3, and then divided by 4. So that is going to be a -1/4, or -0.25. This one here, 4ay, so 5 plus 2 is 7 divided by 4, 7 over 4, or 1.75. But effectively, the acceleration is -1/4, or -0.25, and positive 7 over 4, or 1.75 meters per second to the -2. Okay, so that's the main thing we need to start this question, but it does ask for magnitude and direction. So I'm just going to draw a right angle triangle. I will always do it in the same way, so start at a certain point and then always go horizontally and then vertically. It makes your angle in particular a lot easier to think about. So I'm going to try and go to some scale, so I'm going to do a little bit left, but then quite significantly up, because our bigger number is quite a bit bigger. And then this is my actual direction there. So when you come to work that angle out, it's just going to be a lot easier if you use a triangle where you go horizontally and vertically afterward. So that's 0.25. That is 1.75. So the magnitude, just a bit of Pythagoras. So 0.25 squared, 1.75 squared. We've got this up here. So 1.77 meters per second squared. Got to be a little bit careful with the direction, meaning angle. You may or may not remember, we will always measure our angle unless told otherwise from the positive I/x direction, horizontal direction effectively. So this is the angle we want. Okay, we can't find it directly, very easily. So we're going to find this one first. Call it x, if you will, on the inside. And then I'm going to take that off of 180 to get my overall direction above the horizontal. Okay. So x is going to equal to, so we've got opposite negation, so inverse tan, opposite of negation, so 1.75 over 0.25. As I said, getting the angle, make sure I'm in degrees here, since I'm here. Make sure you get your triangle drawn well, and the direction becomes a lot easier. So 81.87. Degrees. So our actual direction here that we want, I'll call it theta, doesn't really matter about calling it anything, is going to be 180 minus that number. 98.1. And I'm just going to put here above horizontal for just excellent clarity. Okay, so again, horizontal and vertical make it a lot easier. Technically a question where you can think about SUVAT, because the idea behind acceleration really is it's just changing velocity over time. That's where this formula comes from. Effectively it's really the formula, the concept is acceleration is v minus u over t, but it's normally used in this way and this is how the formula is given.